Alright, we have the gradient now here. So now it's time to calculate the Hessian. And so we will derive this function with respect to WK. Yeah? So let's dig into the algebra here. So you have a sum x ij, yeah, does not depend on W, times alpha I minus yi. Yeah? But I need to take the derivative of that. Sorry, forgot. WK and then alpha I minus yi. Okay. Yi does not depend on W's. This will disappear. So we basically have the derivative of alpha I with respect to WK, and that's what we get here. Okay, so we're gonna move this there. Equals the sum of xij, xik, and then alpha I 1 minus alpha I. Now this here we're gonna put in a matrix form is Zj transpose B Zk in this form. Okay. Zj is a row vector, is Z1j So let's now see what Zj is. Zj is Z1j all the way down to Zmj. And Zk is exactly the same. Z1k all the way down to Zmk. Yeah? And this matrix B will be a diagonal matrix, so with zeros here, and here on the diagonal you will have your alpha I times 1 minus alpha I. Yeah, and if we make this calculation, you're gonna see it's gonna be similar than there. For example, so this here we're gonna transpose. So this is actually the transpose, and this is also the transpose. So we keep this row, Z1j, Z2j to Zmj. Then we have our big matrix B. On the diagonal going to be alpha 1, 1 minus alpha 1. Yeah, these will all be zeros. And at the end we have another column vector, Z1k all the way down to Zmk. Now, this is if we write it in a vector. And now we can, let's say the first element is going to be, so this is a 1 times m, this is going to be an m times m, and this is going to be a an m times 1 matrix. Yeah. So this is going to be a square matrix. So we calculate this, we have Z1j times, okay, let's call j is 1, yeah, Z1j times alpha 1, 1 minus alpha 1, and then I multiply with Z1k. Yeah. So when you see the similarity between this one and this one. So indeed, we can write this as a in a vector form. Yeah. So the Hessian equals x transpose B times x. I replace the z by x's. Yeah. So the nice thing here is that, you know, alpha is always smaller than 1, right? Because alpha is this. Yeah. So this element, this matrix, all the elements will be positive. Yeah. Because the sigmoid is positive. Yeah. So this is basically positive semi-definite matrix. Positive semi-definite matrix, and that means that the function is convex, which is a nice feature to have, because it means that the minimum will be the global minimum. Okay, so now we have the gradient and we have the Hessian, the Hessian with respect to W, and now we're gonna apply Newton's method. Just for your information, this should be a minus. Sorry about that. So what we have is that the next W is equal to the previous W minus the Hessian minus 1 times the gradient. This is going to be our update rule, and it's easy to calculate. Yeah. So this is how we find a minimum for the log loss. Yeah. Okay, that was it for logistic regression. I know there's been a lot of math here. Let's jump to the coding exercises.